let me give you a brief recap of where we are at. So the part one was about fluids, and what I call chapter one is buoyancy. And then we started with a very interesting opening question. Actually, we started in lecture one or beginning of lecture two, talking about the goal of physics is to understand how the universe works, and that leads us to the idea of we want to find out how things move. And when finding things move, we need to know all the forces acting on an object, and that basically is the philosophy of 3A summarized, because it's all about how to find forces. At least 90% of that course is about doing that. So here we start off kicking by introducing a new force called buoyancy, which is a force when you're immersed in fluid. It's a contact force. It's not new in the sense that it's something drastically mysterious, because it's just due to contact, pushing on you. And we talked about Archimedes' principle, which is the reasoning behind B equals to rho VG, why that buoyancy force is the way it is. And so we started off that way, tying in from 3A. And then we decided, now that we have the idea of why things flow, in principle, you have the complete theory of analyzing if someone ever sinks to the bottom of the ocean, you can do them a calculation and explain to them exactly why they're sinking to the bottom of the ocean, because probably they need to lose weight, the idea is. And then we move on to a look at just fluids, because we want to study things in a more complete way. So we split that up into look at static ones and then moving ones, right? Dynamic ones. I tend to like to use simple words as much as possible. Using complicated words like dynamic or fluid dynamic, I mean, that's good and fancy, but that's the best way to turn people off and make people think that physics is more difficult than it is. So yeah, and then now, so this is the big picture. It's always good to keep the big picture in mind. And then now we turn to the very vast topic and very important topic of thermophysics. So just like before, let me start off with the opening question, or basically the guideline, the question you should keep in mind. Why do we care about this subject? What is the question? What is the question we're trying to answer with this subject? Because the worst thing is going through a lecture course. I'm sure you guys have been through lectures where they go through technical details after technical details, and you have no idea why you're doing this. I'm sure this is not happening at UCI because all the professors are perfect here, but I'm sure you've heard stories about that. So it's good to understand what you're trying to address. What's the central question you're trying to address? So you have that goal, you have that path in front of you, and you know what you're walking towards, instead of meandering and get lost in the forest, right? So I think here what I would pose as an opening question is just what is heat? In fact, it looks like a very simple question, very innocent question, but this is actually in the scientific history, historically, this is a very important question that has confused scientists and physicists for a long, long time. People have put in so much effort and they go in wrong ways. We'll talk a little bit about that in misconceptions about that, and to find out what heat is. Now, at first it seems like a very basic question or not an interesting question, but you'll be surprised the answer to this, which is the end of, I showed you the syllabus, by the end of around chapter 10, you realize this is the theory that kicked off the Industrial Revolution. This is what made steam engines possible. This is what made industry possible. This is what makes the railway, the car that you probably use every day, and a lot of the modern world kickstarting. It's because people finally understand what is heat, and how do you utilize it to your advantage, right? So that is the goal we are trying to understand the basic principles of, and with that principle, in principle, one could take that further and build upon it to make great machines. However, the second part of that story is usually dedicated to this field of engineering. In physics, we understand the principle first, but it's also interesting that it will bring up a lot of new ideas, very fundamental ideas that make great advance in physics, our understanding of the universe, than just applications in the real world. For example, the concept of energy. People have never understood energy better after studying what heat is. Okay, so as I keep going over here, keep writing, I want you to, if you like, you can type in the chat, what do you think heat is? Put a one sentence answer. What's your first, if you walk on the street and someone come and ask you, or if you have a niece or nephew, at that age, which keep asking you why is this happening? Why does the sun come out on the east? Why is things occurring the way that, why do apples fall to the ground and not fly to the sky? If they run up to you and ask you, well, what is heat? What would you say in the beginning of this chapter, and what will you say by the end of the second part of the thermophysics? We'll see if we can get some ideas while I write. So basically, this is what I call, if I need to write a subtitle, this would be the study of heat. Okay, and there are several things immediately if you start off with a new subject that you want to learn. There are a couple of questions you want to start with is asking, what is it? If someone tell you, I have this new concept called rocket, the first thing you want to ask is, what's a rocket, right? And then the second thing is, what does it do? What does the rocket do? Well, what does heat do? Right, I've see a little answer already. That's a good answer, actually. Good job, Ilaha. And anyone else? Put in one sentence. What do you think heat does? What is the effect of heat, right? Other than make you sweat. Actually, that is one. It does make you sweat. But what else? What do you think? There's no right or wrong answer, just to get you participating. And the third question is, why do we care? The rocket can go to the moon. So why do we care? Right. So you can come up with reasons for that as well. All right. So actually, to give you a study tip, let me put it on the side. These are, or maybe I should say learning tip. When you're learning anything new, I would encourage you to, I'll put a box around this because it's so important. It applies to physics as well as any subject you're going to learn as well. So if you're taking other courses this quarter, you can try to apply this logic to think. Is every time you learn a new subject, ask these three questions. I'm going to rewrite this once here in a different color because of how important it is. That will give you a much better direction, orientation as I motivated in studying, and you will do a much better job knowing where you're heading instead of blindly just memorizing all the details. Okay, so if you're doing biology or chemistry or whatever, try to ask yourself every time you learn something new, if there's a new concept called photosynthesis or ionization or endothermic reaction, whatever. I'm throwing out words that I have no idea what they mean. The first thing you want to do is ask these three questions, right? So let's answer these three questions first. Let's see some of the answers over here. Motion of particle, that is actually surprisingly great. So someone has been doing their pre-reading, good job. A form of energy that can change temperature, that's not bad. Release of energy, exchange of energy, everyone's pretty much on the right track. That's very good job. All right, good. So what does it do? Let's go to the question. Let me call it, yeah, question A, B, and C, because I'm going to use 1, 2, and 3 shortly in a second. What will heat do? I don't see any particular answers, but let me summarize. The first thing, I think there's a hint already. One thing is it will change the temperature. Omar said it will change the temperature. So temperature increases. That's one thing heat will make things do. So it will make the temperature of an object increase. But what do we mean by temperature? Back to that annoying niece that keeps bugging you. You tell them heat will increase temperature, and they go like, well, what is temperature? Explain that to me. Well, we'll do that today, actually. And then, so that's the goal today. And you probably have this experience as well. Volume would increase when heat will cause things to expand, right? So that's another thing. And the third thing is the new concept. And increase the speed of particle. You'll be surprised how correct you are, actually. Another answer from the chat. And one more concept you just learned basically from the first week is pressure, right? Although it's not groundbreakingly new, but we're formally introducing the idea of pressure in physics for the first time last week. So these are actually the three most important variables, P, V, and T, that will be affected. In fact, we're going to dedicate one of these chapters for each. So basically today, which I'll call chapter 4, we'll look at what is heat, and I will answer that questions, which is very similar to the line you guys have suggested. But that is actually the macroscopic view of what heat is. And then there's the microscopic view, which is much more challenging and is to be come back to. Let's see, what is the chapter number? It's chapter 8. So there's a microscopic answer as well, which is a much more modern understanding and deeper understanding of what heat is, a great improvement from the 18th century concept. And then we'll basically dedicate the chapters. Chapter 5 was dedicated to look at how does it affect volume, how does heat affect volume. Chapter 6 is dedicated to how does heat affect temperature. Chapter 7 is dedicated to how does heat affect pressure. And I will mention that all solid, liquid, and gas heat will affect the temperature and volume. However, pressure is mainly gas, because for solid, the pressure will not change a lot when you heat things up. It will change a little bit. So as usual, if we take the simple scenario first, trying to understand the simple case first in physics, ignore the complications, those tiny details, just look at the big picture first. Solid doesn't change much, the external pressure. Okay, we'll get more to that. And finally, we want to look at applications, right? Why do we care? So that is applications. Of course, in each chapter, we'll sprinkle applications into the chapters, so you know why you're doing that. But in chapter 9, the content of chapter 9 is basically the theory of thermodynamics. And this is the fancy word that kicks off the Industrial Revolution. It's the theory they use behind it is thermodynamics. So the final word in putting this all into perspective is, remember in 3A, actually 3B, although as I motivated in the beginning of the course in lecture 1, it's actually it's going to be very intense because there's lots of stuff, lots of new concepts. As you guys saw on Piazza, there's many good questions that after you do your reading, you realize you'll come up with. So it is actually tough in 3B, but on the other hand, the silver lining is it's probably much more interesting if you can get over that toughness. That's why I try to encourage you to focus on improvement and not perfection. Right? Once you get that idea of perfection out of the way and try to just strive for improvement and learning, you realize 3B is much more interesting because 3B is probably much closer to real life. In 3A, the closest thing you study is a ball rolling down a slope, which might benefit you when you go bowling, or I don't know, and understand why does apples fall on top of your head. How often does that happen? But you go swimming a lot, and now you have the theory of knowing why you float. And thermophysics, especially nowadays in summer, it's still early right now here in California, but in midday it's getting hot, so you know what happens there, and you have much more, it's much tying closer to real life. And that's also why you see a lot of the examples in the lectures I do is about estimations. I want you to be able to take the concept and apply it to real life. Problem solving is good for exams, but what ultimately you want to do is to be able to benefit your life in some way after learning this course. So estimations is one thing we sneak in, right? Already, even in fluids, you see there are good examples, right? So, and I know a lot of you are not going to be a physicist or engineering, maybe you'll become a doctor, but you just never know when will these concept comes in, other than the soft skill of, learning to self-learn, to able to study on your own, all those soft skills. Also the hard skill, you never know. Like we talked about if you measure blood pressure of someone, or you understand that we are all actually under a lot of pressure from atmospheric pressure. It's actually a huge amount. And the only remedy for that is inside our body is the same pressure as outside. So there's no pressure gradient. So no pressure gradient means no delta P, right? No difference in pressure means no net force due to the air, at least. Due to this atmospheric pressure, there's no net force. Otherwise we'll be crushed, right? So if in the future you become a doctor, you have a psychologist or something, a patient come in and tell you they are under a lot of pressure, and you'll go like, so am I. They'll probably not appreciate that, so that's why I'm not a doctor. But or if you have a patient, that is suffering on obesity, and they want and you need to lift them up on the bed. You know how to construct a hydraulic lift, so you can push with one finger, and then you can put them on the bed. You just never know, right? Or since we're in LA, and people might come in and tell you, I want to lose weight, and you can tell them, well, I have a simple solution. You don't need to go on a diet. You don't need to do a lot of tough work. It's very simple. Just jump in the water. You realize your apparent weight is immediately less. Put a scale underneath you and step on the scale, right? Or pull on a tension of some scale. Try to read the number. You will immediately have a smaller weight. Right? They may roll their eyes and say, well, okay, that's apparent weight. If they have took my lecture, they'll go like, that's apparent weight. I want, and you can tell them, even you're standing in air right now, you're in that, when you stand on the scale, you're measuring your apparent weight. What you want to lose is not weight, you want to lose mass. Now you need to go on a diet, okay? So I'm sure your patients will love you for that. All right, so let's go in chapter 4 and call this Introduction to Thermophysics. And the reference chapter for this is in the textbook 19.1 to 2 and a little bit about 10. Okay, so as we go on, you'll see me put brackets around chapters or sub-chapters from the textbook. What I mean by that, I'll remind you a few times, is that means limited examinability. Okay. So these are sometimes either the start chapter in the textbook anyway, or just due to the nature of a summer course, we won't be able to do everything in excruciating detail. That would just give you extra pressure, no pun intended. So there are we'll make some choices of what's more important and what's less important. But it is part of learning. So when I put a star, also you see in the syllabus, if you study that already, you see that some of them I put a bracket around and said limited examinability. That means what I want you to get out of those chapters is the rough idea, the rough concepts. And most likely, let me just say usually, it will be unlikely you'll see an exam question on that, okay? So I'm sure immediately some of you will go like, yes, I just forget that. I respect that. That's fine, because getting a GPA is also very important. But if you happen to have a spare time, you know, a few minutes before you go to bed, and you just haven't got enough physics of the day yet, and you just need to do a little bit more, feel free to do some casual reading on that. You might be surprised to find anything interesting. So there will be no detailed problem solving tested on that when I have these limited examinability chapters. Okay, all right. So first, we were trying to ask, in this chapter 4, we were trying to ask what is heat, right? So here's another guideline for you whenever you learn new things. The first thing, whenever you learn something, this is what I think is really important, is you need to know the definition, okay? Definition can be, so any subject, even if you go in chemistry or biology, you want to do that. In fact, this is something that all biology students know. When they flipped in the new chapter, the first few paragraphs is full of definitions. You learn new words like diaphragm, or again, I'm throwing out words, I have no idea what they mean, but definitions is something very accustomed to. But for some reason, a lot of students, when they go from biology and then they go into physics, they suddenly forgot that this is actually one of the important steps. And it's because I think sometimes a lot of lecturers don't emphasize this enough. That's what I want to try to do. And okay, so that's the general skill. Specific skill for physics, there's 2 ways to do definitions. It's you can learn it in word form or in equation form, right? And both ways is acceptable in the exam. That's why I want to test that, because I think it's the #1 thing you should do in learning any new things. And I think the best analogy I've came up with in explaining why this is important to people is, imagine you're reading a novel, reading a fiction. Imagine you have to read, say, I don't know, Harry Potter, and every other word, you don't know what it means. You will never get anything out of that story. You will not be able to enjoy the story. You will not be able to enjoyment aside, you won't learn anything new. I'm sure we learn so much new to our lives in Harry Potter, right? So if you don't know what the words mean, you can't understand things and you can't learn it. So I can't stress enough how important definitions is. And this is sometimes misleading, because in physics, we use words that are very simple, and it looks like everyday words like heat, or even work done, or energy and force. And it gives the illusion, there's good and bad. The bad thing is it gives, well, okay, the good thing is, it's the reason why I can never succeed in biology, because I am so bad at spelling. So you guys who are doing so many biology courses, you have actually my utmost respect. Learning the words which are longer than 5 characters, I have trouble with. So in physics, we put the cookies on the lower shelf, and we use the words so simple that you don't need to. No, remember the 4 types of fundamental forces in physics, other than gravity and electromagnetism, is the nuclear forces. Brilliant idea, physicist idea, let's call them strong force and weak force, because one is stronger and the other is weaker. So we use simple words. The bad thing is it gives the illusions to newcomers, learners in physics, that they think they know what a word means when they forgot, then when they do not realize is we actually mean it in a technical sense. And we could have called this thermology instead of heat, and then give you a definition. But you know, what do you prefer? Do you prefer we call it heat with the proper definition when we in the textbook, or do you prefer introducing a huge word? I don't know about you, I prefer the simpler one. After that, the next thing after the definition is try to explain in layman words, in layman terms. Layman means someone who haven't studied the subject technically. So this is technical, because you're a student after all of this course. So by the end of it, we want you to learn the scientific side of things, right? But that doesn't sometimes help. For example, shortly, I'll go to the definition of energy in a few slides. And then what's the definition of energy? In physics, the proper definition is the potential to do work. Is your life any better off from that? Not really. Can you do more physics solving problems? Yes, because it's formal. But it doesn't help you understand. So to develop an intuition, this is important. This is important in developing intuition, which someone can argue is the foundation of understanding. Understanding is not about reciting and regurgitating all the formal definitions, but it's about getting an intuitive idea of how that concept can be relevant to you. So a good litmus test is always think of your 5-year-old niece that is trying to bug you with every question. Can you explain things to them? It might not be technical, it might not be so precise, but it will give them understanding, and that's what we need. Okay, so a lot of people skip this step. And in some sense, I always have no surprise when people struggle in physics when they skip this step. Of course, you don't understand physics if you've never done this step, right? So it's not a judgment on anyone. It's a skill that I want to teach you. And then hopefully after this, for the rest of the 4 weeks, you'll start to see that physics becomes easier and easier if you follow this algorithm. And then the third thing is, what is the quantity of interest or about it? I'll just say what is the relevant quantity, okay? In some sense, that is how to measure it. Let's say now you know what heat is. The next question is, how do you measure it? Because if you know what something is and you can't measure it, that your life is not better off in any way. You might as well not knowing what it is. So this is the experimental and scientific side of things. So this theoretical physics, right, and experimental physics, the theory side, as a theoretical physicist myself, we're often being accused of not being realistic in the real world, and we come up with ideas that are not measurable. We get a lot of flack from from experimentalists, but it is important, right? So just in our defense, we know that, we just don't want to do it. I'm kidding. Yeah, so that's that. And then the fourth thing is its relationship with other old concepts, quantities that you've learned. So when you learn a new concept, the idea is, after you know what it is, after you get an intuition, after you know what is the scientific way to measure it, so you have a concrete idea on that, the last thing is, how does this tie into the big picture? How does it tie into things you already know, the old concepts you already learned? We're going to learn heat in this chapter, and then chapter 5, 5, 6, and 7 is about now, how does heat relate to things that we already know in chapter 1 to 3, and also from 3a, and gain an even deeper understanding of how our world works. So how do you do this? This is the step in learning all the formulas and relations. Formulas is basically relations. Imagine chapter 1, what's the new concept you learn? You learn buoyancy, right? And then we have a definition for buoyancy. It's the upward force. Upward force, we only have a word definition for it, but whatever, I'm not going to write that out. We have an upward force due to surrounding fluid. It's a contact force, right? That's the definition, what it is. And then the next thing we learn is a formula for it. Because you already know what density is. You already know what volume is. You know, from 3a, you know what volume is. You know what acceleration due to gravity is. And then with these old, now you have a formula that link this new concept that you just learned with old concept. Now, so many people directly just jump, when they study physics, they jump directly to the final step and skip the first 3 steps. And then they will tell me they don't understand physics. And I say, yes, you don't. If you want to, this is how you do it. So many people jump right over here and find physics confusing. And then all they think physics is about plug and chug, and they forgot about what is really making physics in the first 3 things, okay? All right, just a small comment is density. Technically, I introduced it after buoyancy. Actually, no, sorry, I did not. Yeah, I did things in the right order. Yeah, that is also important in physics. So you want, it's always old concept building on new concepts like that, okay? So back to heat. So I think some of you already got the right idea. It's motion of particles or vibration of particles. It doesn't have to be vibration. Vibration is just one example. But here, I'll give you the rough definition, rough idea first. So this is what you can tell a 5-year-old kid. It's the motion of molecules or particles. Particles is another word that sometimes confuses a lot of chemistry and biology students. So hang on there. I'll get to define it more properly. And a more accurate version is this. Is the transfer of internal energy due to difference in temperature. Let's split this up into 2 parts. Transfer of internal energy is what I think is the important statement, and due to temperature difference is the fine print. Why do we need the fine print? Transfer of internal energy, if I just smash an object, I will be giving it more internal energy. I'll define internal energy in a second. But that's not technically heat. But if I put it under a Bunsen burner and then now it gained more internal energy, that's heat. That's why the fine print is there. It's due to temperature difference and not due to me taking the object and throw it really, really fast so it gets more energy, something like that, right? And quick comment on the history. I encourage you to read a little bit more about that in 19.1 to 2. So I won't write too much stuff down, but I'll just say a few words. I'm glad no one actually put out the word fluids from the chat, because that was actually the prevailing theory for a couple of decades. All the brightest minds in science and physics think that heat is a type of fluid because heat always flows from hot. You see the word flow, right? We even use the word flow, from hot to cold, hot object to cold object. And if you wonder why this chapter comes after fluids, It's precisely, well, that's not the real reason, but it's almost misleading you to think that heat has something to do with fluids. That is one of the biggest misconceptions. It is not. And if anything, so I'll just write the summary of that. Heat is, so in the past, people think, but if I need to summarize heat in one word, the right word is energy. And this basically, the first guy who realized this is the guy named, you all heard of him, Joules, believe it or not. So this guy, Joules, who was the first guy who realized that heat was probably not a fluid. In fact, this theory was so compelling for so many decades that people think it's true. They give it a name. It's called the caloric fluid. I think caloric has some French or Roman roots that means heat. A word of calories come from this caloric fluid. Like calories we still associate with heat, but we forget its origin. The origin of the word calories is actually a misunderstanding. Joules realized that if you take a box of fluid and then you put some paddles over here, and then you tie a string around it and then tie an apple next to it and then drop the apple or a very heavy weight, whatever, right? So some very heavy weight and you drop it like this, the paddle starts to spin. When the paddle spins, and then you can measure the temperature of this and the waters heat up very slightly, but it heats up. Now, if heat is a fluid, this is impossible. This is what tipped him off in realizing heat is energy. Because here, you see the weight is losing energy. It's going from a higher gravitational potential energy to a lower gravitational potential energy. So when it loses energy, where did that go? Because the way it is connected, it's in this genius experiment, in this genius setup that he connected, he have transferred this gravitational potential energy into the water, which warmed it up. And this is what tipped him off in realizing, oh, heat might actually just be a type of energy. It's just like I'm translating gravitational energy into a kinetic energy. I'm making things go faster when I drop it, right? So things goes faster. So energy can be transformed, but it cannot be created or destroyed. Now, if heat is a fluid, so matter cannot be created and destroyed. You've all heard this. If heat is a fluid, now this experiment over here, I'm creating heat, I'm creating fluids, the caloric fluid, whatever that is, out of nowhere, just by dropping something. Imagine if you drop something and you can create any object. That would be a great money-making machine, right? So that is why he was able to go against everyone's belief and convince the community that it is energy. Next question. Notice we got the definition. We have a rough idea. The layman word is energy, okay? Or motion of particle. That's also good. We'll relate the two later. Okay, what is the quantity? So the quantity, first thing is, before I put a tick on that, you want to know the name of the concept. So here with defining heat, let's give it a symbol. The symbol is Q. I'm leaving a small space in front because what I'm going to show you is I like to write delta Q almost every single time. You'll see the benefit of this later on. But the textbook will just write Q, but delta Q has so many benefits. Number one, just to show, the first one I can already show you here, but it's not limited to this, is look at the definition. It's a transfer of energy. Okay, I need to define what this internal energy mean, but it's a transfer of energy. So it's going from one place to another place. Some guys gaining heat, some guys losing heat. It's always a change. So heat, putting this green delta in front, right? If you remember, delta is the mathematical symbol of change in, right? It translates to. Emphasize that it is a transfer, and you won't, it always needs to be, Q always has to be something minus something, right? So if Q is always minus something minus something, might as well put a delta to emphasize, remind us. A lot of students make the mistake of analyzing the heat of something. That is not a right grammar. You can never talk about the heat of the water, as you will learn. People do that all the time in real world, but then again, we also call weight mass, and mass weight, by the way. So, but, right, so yeah, you cannot talk about the heat of something. You can only talk about the heat gain of something. Okay, we'll see more as we go on. And how to measure it? Well, so you need a quantity. So the quantity for heat is you measure temperature. Technically, it's the quantity of a heat, but heat gain or heat loss is in terms of this idea called temperature. Notice we haven't seen this. This is a new idea in terms of the physics sequence. I know you know what temperature is, but in terms of this, right? And the device that we need to use is a thermometer to measure temperature. Okay. A few extra comments over here. You will hear me and in the next 3C and other physics course talk a lot about quantity in physics. What do we mean about quantity? A quantity is something we can measure. One thing why students find physics confusing, another thing, is because a lot of professors use words without realizing they didn't explain what they mean. You must have heard quantity, and then they repeat the word quantity and then assume people know what it means. But let me define it once and for all, because some of you might not, and it's not obvious. So it's something we can measure, something we can quantify. Okay, what that means is something you can assign a number. So for example, velocity, we give it the name V, position X, acceleration A, force F. These are physics quantity, anything that you can measure. Now, buoyant force is a quantity, right? I call it B, the textbook call it FB, someone else call it something else, it doesn't matter. That's a quantity. And then the concept of buoyancy is not a quantity. Buoyancy is the concept, right? It's a qualitative concept. The quantitative part of it is buoyant force, right? So that gives you the idea. So even if you know the idea of buoyancy, it doesn't mean you know how to, if you want to do actual calculation with things, you need to know the quantity, okay? And after you know the quantity also, so now the quantity is temperature. The symbol we use is T, capital T. And the next thing to learn is the SI base units. And it's Kelvin, which is very related to Celsius, less related to Fahrenheit, but Kelvin is the formal base unit. And I'm going to say this advice, problem-solving tip advice many, many times throughout the next few lectures. You will hear me give you this problem-solving advice is when in doubt, change everything to Kelvin first. This is the same advice I give with change everything to SI base unit, because I can already tell you there is every time I teach or TA this course, I get 100 questions people ask, when do I use Celsius and when do I use Kelvin? At least they have the sensibility to not use Fahrenheit. But when do you use what? I will tell them I have two answers. Number one, if you are unsure, always change things to Kelvin in the get-go, in the very first step. You will never get it wrong. That will be 100% correct. Now, the quick way is sometimes in certain cases, you can just keep it in Celsius and it will work. Sometimes it cannot. Okay, if you know when to do which, if you have studied this and after the end of the quarter, you will understand it so well that, okay, if this time I need to change it to Kelvin and I change it back to Celsius, and I know in advance that I'm just doing redundant work, then you can keep it in Celsius. Okay, so that's my two answers. If you know what you're doing, then do what you know to do. If you don't know what you're doing, change it to Kelvin. That will 100% be correct, right? Other than wasting you extra 30 seconds, that's it. All right, so now let's talk about three words that are often treated as very similar, but have very subtle difference. And I apologize if it's going to be a little bit dry for the next 20 minutes because it's going to be a lot of definitions because we're learning new chapter and we have a lot of definitions we need to introduce. So heat, internal energy, and temperature are all different things. Okay, so right? So all of them. Let's clarify what does this mean? Heat versus internal energy versus temperature. Now, energy. First, let's address internal. It can be classified into external and internal. External means it is to do with movement. Either do with movement or it's under the influence. It's a type of energy. So this is types of energy, two types. Let me just say type. External is either due to some movement or due to the influence of a non-contact force. For example, gravity. So if you have gravitational potential energy, that's considered external. Okay. For example, gravity. For example, electromagnetism. For example, the electric force, right? So here's a diagram, right? So if you have an object that is moving at some velocity, right? So you have kinetic energy. If you have an object that is at some height away from the ground, so if that's the ground and you put it on a table, it doesn't have to be falling, you just put it on a table. Just the fact that it's above ground, it has more energy than it is lower ground, believe it or not. This is again a new idea that Newton and his friends, so Newton and friends found this out. It's not obvious because it's not moving. Why would you think it has energy? But he realized it has energy because as soon as you push it off the table, you will see it turns into movement, right? So you're gaining movement, which is energy, just because from the fact that if you're lower, you'll gain less movement. So the higher you are, you actually have energy. So it's called potential energy, right? It's the potential to become movement. So this is due to non-contact force. So the mere fact of it being high, so something having a velocity will give you kinetic energy. Something that has height will give you gravitational potential energy. Now, I'm emphasizing gravitational because later on we'll realize if something has a charge, let's say this is positive, and then you have some negative surface over here, right? There will be an electric force try to pull this guy this way. let's say you hold it still, you don't allow it to move, but as soon as you let go, you will believe me very quickly, it will translate into kinetic energy. So there is energy there, even though even if I nail it down and it's not moving, because as soon as if the nail just breaks, boom, it will immediately turn into energy. So it must have some potential there, and that's called electric potential energy. This is what next week is about, or the end of next week is about, right? So you see, any force gives it, there's a magnetic force, right? The same idea, I'm not gonna draw a diagram for everything, but later on we'll realize this is actually the same side of two sides of the same coin. And there's some nuclear force, right? We talked about the strong and the weak nuclear force. Anytime it's under these forces, these are external, so some external influence or movement. Internal happens is a type of energy that exists, it's energy it possesses even when at rest. Keyword is this, right? At rest. So even when it's at rest, you have energy. This is internal energy. So a diagram I can draw to that is, all right, this is just doing its thing, right? It's not bothering anyone. It's just standing here. Believe it or not, this is very counterintuitive. It's a big discovery that this actually has energy. And that is what we call internal energy. And how do we measure internal energy? So sometimes called E-int. You'll see the textbook use the word E-int. So how do we measure it? Remember learning new concepts? Ask yourself what it is, and then what's the definition? I haven't given you yet, but I will in the next page. Let me jump to how do you measure it? You measure it with temperature. All right, so now I haven't got to heat yet, but I've differentiated what's internal energy and temperature. Temperature is a way to measure internal energy. Temperature is in Kelvin, internal energy is in joules, the SI units. So temperature, let's define that, is the measure of average kinetic energy of individual particles in a system. Okay, so the key word is it's a measure of average kinetic energy. The fine print is of individual particles, okay? The thing that just makes the grammar a little bit more complete is inside a system. Okay, a couple of new words over here. Kinetic energy, you know what that is. A system is a word I will use a lot. In the past, I will use the word objects when you study something rolling down the slope and something like that, right? But now we have, for example, in this chapter, we will study things, not one single object, but we have a box, and then there's particles, either moving, right? Either spinning around and doing its thing, or it's vibrating left and right, up and down like that. So there's lots of objects in this box, right? So it's a little bit unfair to call, when I say object, do you mean the whole box of a lot of Avogadro numbers of particles, or do I mean the individual particles when I say object? So let's use the word system. Then I'm talking about this whole thing that is at rest, okay? So I can talk about energy of the temperature of a system, which means I stick a thermometer into this thing and then find out. So kinetic energy, let's understand that first. So there is actually 3 types of kinetic energy, which I have actually drawn over here. The first one is translational, it moves. The second is rotational kinetic energy. Rotational kinetic energy. And the third type is vibrational kinetic energy. So kinetic energy is the energy of movement, as I mentioned over here, right? So there's these 3 types. Basically, you can classify into these 3 types. All of these 3 types can be contributing. So all of these can contribute to temperature. If it is a gas, which one is the most important that contribute? What is the dominant type of kinetic energy in a gas? Can you guess? How about solid? They're the 2 extreme ends. For gas, the most important type is translational. Should be pretty obvious why that is, right? Gas particles move around. For solids, do the molecules and atoms move around that much? No, but they vibrate, right? So the temperature is contributed by vibrational kinetic energy. Okay? So as you can see, all contributes to temperature. You're already learning something new, right? So, and lastly, so that's the word system. How about particles? You hear that a lot, and I guarantee you, again, every time I teach this course, so let me address it right up front in the first lecture, is the question is, what is this particle that you physicists always talk about? In chemistry and biology, we talk about atoms and molecules. We talk about elements and compounds. We talk about ions and stuff like that. What do you mean by particles? You know what the answer is? All of the above. We don't care. Physicists are that lazy. Anything that is basically looks like stuff that the more formal definition, I'm not going to write everything down, otherwise it'll take us all day, but I'll just read it out. Anything that is indivisible during the question of interest, then we call it a particle. So that can mean atom, it can mean molecules. We don't care whether it is made of one thing or three things connected together. As long as in the problem of interest, the three things do not break apart, we'll call it one particle, let's say H2O. As long as when I'm heating it up, as long as I don't go so far as to break it apart, it moves, as far as I'm concerned, it moves as one object. I'll just zoom out and turn a blind eye to the details. That's why physics is simple. You turn a blind eye to any complications, and then you just call it a particle. Well, it could also mean, I don't care what chemistry jargons. If you're a chemist, you might be very picky about, oh no, that's an ion, or it's made of one thing, or it's made of more things, elements or compounds, anything. If it breaks up, I have to worry about that, yes. But as you can see in most of the cases in our studies, it doesn't. Does it have to be this small? No. We can talk about dust particles. Because if I'm analyzing the motion of dust in the room, that's completely fine. Let's take that further. To us, a baseball is a particle. If I'm throwing a baseball in 3A, because what you do in 3A is throw baseballs, as you all know, then does it break apart halfway in midair? No, it doesn't. So you actually might or might not have heard of this word used there already. That's what it means. You can go further. It can be a football. It can be a bowling ball. It can actually be bigger, and it can be the moon. It can be the Earth. It can be the galaxy. I can go further. You think I'm being ridiculous, but if you're studying astrophysics or astronomy, we treat the Earth and the moon as a particle system. Basically, that's why physics is so powerful, because if you understand the motion of particles, remember the ultimate goal of physics, it applies to almost everything else. The same principle applies to Earth as to atoms, essentially. You might need to improve a better overall theory, but once you develop the theory, it should apply to everything, okay? And my research is in quantum gravity, and I look at the cosmological effects of how does quantum gravity affect the universe? What does it do? Do it pull things together? And basically, what we do, believe it or not, we treat all the stars and galaxies everywhere as just dust particles. It's essentially treat it almost as a dust, because it's an object that it doesn't break apart as long as it moves around. That's what we mean about particles, but pulling ourselves back to Earth, this is most likely what we're focusing on in this chapter, or in the upcoming chapters, atoms and molecules. We don't care about that. Is that clear? So hopefully that's clear. All right, so let's do an example. So just recall, so temperature is measure of average kinetic energy, and then all those fine prints, right, of individual particles. Actually, that's important. Individual particles of a system, right? So let's say I have this system of this thing rotating, moving, or vibrating, right? I can have do all at the same time, right? I have a box over here. So let's say this guy has 1 joules of kinetic energy. This guy is rotating with 2 joules. This guy is rotating with 3 joules. My question is, what is the average kinetic energy of an individual particle? Actually, this is important. Individual particle. What's the average kinetic energy? Well, there's 1, 2, and 3, so the average is 3. Sorry, 2. So the average is 2 joules. So each particle has 2 joules on average. Okay. The reason is because when you have an Avogadro's number of particles, you can't really keep track of every single thing. They bump into each other, and suddenly one will have more and the other will have less. So we add everything up, divide by the number, right? You get just an average like this. So 1 + 2 + 3 divide by 3 is 2 joules, like that. Okay. So temperature is basically a device, or it's a quantity. So a thermometer is a device that takes the value of 2 joules and translate that to X Kelvin or Celsius. So this is what a thermometer do. It's doing this conversion. It's basically converting joules to either Kelvin or Celsius, or whatever your favorite temperature unit is. Okay, in some sense, people can argue that actually the idea of temperature came before people realized things are heat is energy, and because they have been measuring, they make mercury thermometers and etc. and measure things. And now that we have a deeper understanding of it, we think this is actually a waste of time. It is much better to measure temperature in joules. Right? Because a lot of formulas, it's basically something like this: E = KT, where K is something called a Boltzmann constant. It's just a constant in all of thermodynamics that we use. And you see, if E equals to KT or something KT, whatever your formula is, you have like maybe 3/2, and then blah, 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 whatever. And then you see KT inside. And so whenever you see it relating E to T, you always see a K in front of it. That's because it's to take the unit to convert it from one to another, Kelvin to joules, like that. Okay? So it's a waste of time, and people argue that we should just measure temperature in joules, and then all your formulas would be much simpler. Like if you have a more complicated formula, then okay. So if I half the temperature of something, then my new energy would just be 1/2 T or whatever, something like that. You don't need 1/2 KT. And in fact, this is called natural units. And basically, if you do any theoretical physics, which I'm sure at least one of you will go into after this class, we actually always use natural units. So in my daily life that I do every day, if I do need to talk about temperature, when we communicate, we don't even use Kelvin. We don't use Celsius. We use joules, because it immediately tells us temperature measures energy. Okay. And all right, so let's ask one more question over here. So what is the total energy? Total internal energy, right? So we can write E total internal, let's put bracket. Total internal, what is it? Well, you have 3 particles, right? So it's 3 times the energy of individual particles. Okay. So all of them are going to be internal. So we're not going to talk about external, right? So this is going to be internal, the total internal energy, the total individual particles, the individual internal energy and the total internal energy, right? So because this is average, right? So you take the numbers, multiply by the average, you'll get a total. So it's 3 times 2, and the total is 6 joules. That's the answer. So E total equals to 6 joules. Very simple. Now you might say, well, you asked total, so why don't you just add up everything? Why do you say 3 times 2? Why do you use the average instead of just doing 1 plus 2 plus 3? Well, this works for my case here, but imagine you have a glass of water. Now it's your job to add up every single particle, H2O particles, H2O molecules, right, in the water. You would rather find the average of one particle and multiply by n. So in general, E total, internal. If it's obvious it's internal, you can drop the label. But I'm just going to emphasize, it's n times individual particles, internal energy. Okay, again, very simple, but it's a concept that you need to clarify. All right. Okay, so now let's do this. If each molecule, so let's try a new example. So, to see if you understand what this means. So if each molecule, I'm going to use the word molecule and particle very interchangeably, all right? So yeah, let me just start to get you used to the idea, and I'll use the word particle. Has E equals to KT, as I alluded, right? The K just translate the units. So yeah, I'll talk more about what K is in the future. That will be in a few chapters' time. What is E total if a box, which means if my system has 100 particles? Let's cut it. Question A. Question B. If each particle has E equals to 1/2 KT, what's the E total? Question C. If each particle has, the individual particle has 3/2 KT, what's the E total? And try to put these answers on Piazza, and then each other you can, it's almost trivial, but yeah, just to make sure you guys understand this. Okay. All right. So now, finally, so we understand what internal energy is. We understand what temperature is, right? Internal energy, I just talked about right over here. It's basically with the energy that something has when it's at rest. So as you can see, the word internal, right? All the kinetic energy is inside. It doesn't cause external movement. We talked about what temperature is. It's a way to measure internal energy. Finally, heat. Right? So we'll answer the goal of today, which is what is heat, right? So heat is, as I mentioned, the symbol is delta Q, is the transfer of internal energy due to temperature difference. Okay? Transfer of internal energy due to temperature difference. Okay? So in some sense, if you like, you can almost write delta Q in symbols is the change in internal energy. But this is a caveat. I don't actually suggest you write this down yeah, because there's the first law of thermodynamics, which is a little bit, in case you get confused, because the total change in heat or the total change in internal energy is the amount of heat you put to it plus any extra work some external work you add to it, right? So that will create the internal energy. But essentially, if you don't have external influence, then delta Q is just equals to this, right? But just to, because this is going to lead to a confusing topic, temporarily, I suggest you not to, well, work out the equation definition, but just use the word definition. All right, so we've talked about this, we talked about this. So transfer, so finally, so you know what heat is, this is it, right? This is the definition. So let's talk about some properties of heat. So in fact, so there's three types of ways that you can transfer internal energy. Oh, sorry, let me give you a diagram. So object 1 in object 2, let's say this is hot, this is cold, right? So what that means is when it's hot, it means it has high internal energy. When it's cold, either high average kinetic energy or high total internal energy, it means it has a lower internal energy. And then when you put it together, the heat, what will happen is basically some energy will get transferred from this side to this side. That's some energy transfer. And this is what we call heat, right? The textbook would just use Q. I like to just have a, the symmetry, right? Delta E delta Q, that's not bad. Yeah. Okay, so this black arrow represents heat. Okay, so what are the three ways this can happen that can go from high temperature to low temperature? If you haven't, in case you're living under a rock or something, you don't know things go from high temperature to low temperature. So three ways it's not a trivial question, by the way. We need to understand why that happens. And just a spoiler alert, we don't. Believe it or not, in physics, some of the simplest questions is the deepest questions in the world. And it's actually what keeps us awake every day to try to find out how the universe works this way. So three ways. Conduction. These are pretty simple, so I'm going to go pretty quick. Convection and radiation. All right, so conduction is by material contact. Okay. Convection is by material transport. So if you have an object like this, if this side is hotter than this side, let's say this side is point A and point B, right? This side is colder. If this is in contact, right? This is one object. So what happens is the heat will go from this side to this side and sort of move that way. And this is conduction. This is transfer by conduction, right? And by transport is, let's say if you have a glass of water and you put a Bunsen burner on one side so that this side is warmer than this side, what happens is this actual molecule would move, this actual particle, H2O particle would move around, this actual particle would move around, and then each particle would sort of move around like this until they equilibrate or become equilibrium. So the whole thing is one temperature. So this is convection currents. That's why if you heat up the glass of water just on one end, the water will start actually moving around and cycling. Try to put a piece of wood next time on top. If you go walk in the lab, try to put a piece of wood there, heat up one side, you start to see it start going in circles because water start stirring in circles over there. So that's one way to make the heat transfer from point A to point B and A to point B. And radiation is by or via electromagnetic waves. This is by far the coolest one. And also the one we will talk the least because it's a little bit more out of the scope of this course. But it's to use a carrier. This is a term, you heard about carrier in biology, right? Especially in these days we live in, right? But what's going on is, if you have two objects separated by even vacuum, the vacuum of space, right? If this is hotter than this, if point A is hotter than point B, right? Object A is hotter than object B. What happens is object A radiates electromagnetic waves. Actually, it radiates in all directions. B will also radiate, but because A is hotter, it radiates more. So let me just draw one side rather than making it too confusing. And what happens is you will have these electromagnetic waves, which is, if you heard of the word photons, right? It's made out of photons. It's basically the particles of EM wave. Each particle, these are little bits of photons, these little particles will carry, they're not they're not the typical particles that has a mass, so they're massless. So it's just an idea to think about. So let's not get too far into that, but they take the heat from A to move it to B. I should say take the internal energy. Oh, after we know these technical difference, by the way, I sometimes might, abuse of language, this is called, just in physics. Sometimes when you know what we're talking about, we might be a little bit sloppy about the actual language. Right? So I should say it takes the internal energy from A and move it to internal energy of B. These electromagnetic waves carry energy, right? Light is a type of electromagnetic wave, right? So it carries light energy from the sun to your eyes. So yeah. All right. So these are the three ways. Now, let's talk about two fundamental properties, which we call laws. Okay. So one is this. The first one is, if the temperature of A is the same as the temperature of B, and the temperature of A is the same as temperature of C, then the temperature of B is equal to the temperature of C. Okay, what is that? So it means that if temperature of A is the same as temperature of B, and A is also the same as temperature of C, then what this law tells you is these two are also same. Okay. All right, you might say, duh, that's obvious. But so what is this talking? Why is this useful? Let me talk about why is it useful first. Why is the concept useful first? The concept is useful. Why the concept is useful is because you can now using this concept, you can compare temperatures. In fact, you can use this to define the term thermal equilibrium. So when so imagine you don't have this concept, and I give you a glass of water, and a piece of metal, and I say they are the same temperature, right? And you go, and I tell you, can you prove to me they are the same temperature? Can you let me know, deduce that they're the same? Can you prove it for me once and for all, without a doubt, that they're the same temperature? You have a hard time doing that, right? Because if you, for example, if I say, let me touch this and touch this, and they feel the same, that's not science. It's not science. They're not scientific, right? And now if you take another colder object, and so if you touch it and you feel it's hot, what's happening is the energy is going into your hand, right? If you are colder and there, so the energy is going to your hand that way. Now the object will lose energy, and then your hand would be a little bit warmer. The object will be a little bit colder. If you touch B again, how can you be sure they are the same temperature, right? Back when you were young, when your mom needs to take your temperature, if you feel sick, she would put one hand on your head and put another hand on her head, right? And then try to compare that. What's going on there is, if there's a more scientific way to do that, is to use a thermometer, because a thermometer is so sensitive that it will, if you put it to the temperature of something else, it will immediately adjust to the same temperature of that guy. Technically, the object will lose a little bit of energy into the thermometer, but it's so minute. So a thermometer is designed that way so that it doesn't take away too much, right? When you put your hand on someone, it will probably take away more. So you put an object that's called a thermometer, right? So you touch it here, you contact with this, all right? So now, and you put a scale over here so that it actually gives you a reading. And then as soon as you touch it with this again, and if it gives you the same reading, there you go. You know that they're the same. So that's what it's useful for. Now the next question you might have is, isn't it obvious? Well, yes, but physicists are very pedantic about trying to prove everything once and for all. Okay, so we are very pedantic about proving everything so rigorously that there's no point of no chance of any error, right? So that's why we need to. And turns out what happens is this statement that I just made over here, people have tried it very hard, but it's unprovable. So you need to treat it as a fundamental law. Okay, so it's that's why we introduce it. Okay, so it's actually so laws are statements that are not provable. Okay. Now I should say not historically provable, because sometimes it's just because we're not smart enough. And then Newton's law of universal gravitational law, Gmm over r squared, he did not prove it. He called that a law because it's the law of the universal law of gravity, Gm1 m2 divided by r squared. And then a smarter guy, his name's Albert, came along and actually proved his law, right? So you can later on in history, you can actually find, if you dig deeper and deeper into theoretical physics, you can actually find out where these laws come from. It doesn't have to be fundamental. It's actually coming from something even more fundamental. Spoilers, it's something to do with the continuum of space-time. It's a fabric of how space-time works, gravity, which is fascinating. So number 2 is, if TA is larger than TB, then the heat will flow from TA to TB. Again, you might ask, is that obvious? You know the answer already. I need to state that. Turns out this is not provable, okay? So if I have, again, in pictures, because we like pictures better, let's say we're talking about conduction, and like this, right? TA is larger than TB, then the heat will move from here to here. Again, when I say heat, I should say thermal, internal energy, but you understand, right? Okay, so these two laws are so important that this is called the second law of thermodynamics. And this is called the Zeroth Law. It's a funny name, I know. This is interesting. It's technically, there's actually 4 laws. There's law number 1, 2, and 3, and then there's 0. People came up with the 3 laws of thermodynamics, law 1, 2, and 3, and then they realized, actually, we can't actually prove this Zeroth Law over here. It has to be a law, but it's so fundamental, we should put it before everything. So we call it a Zeroth Law. So there's these 4, it's like Newton's law of motion. You have 3 laws of motion. In thermodynamics, you have 4 laws of thermodynamics, okay? And yeah, so how about first law and third law? We'll leave, like, that's a future lecture. And a few terms. There is the idea of dynamical or mechanical equilibrium. It's what you learn from 3A. It's basically, so there's 2 types of equilibrium, sorry, that's what I want to say, and there's thermal equilibrium. So mechanical equilibrium is, the definition is when F net equals to 0. Thermal equilibrium is when there is no heat flow between 2 objects, 2 systems. Okay, so in equation, that is in words, in equation is delta Q between 1 to 2, right? Let's call it just delta Q 1, 2. So the heat go from 1 to 2 is 0. Equilibrium. Okay. So, now, one thing to notice over here is this is about one object. The force, all the forces on one object has to add to 0. Then it will be equilibrium. Here, you need 2 objects to define equilibrium, right? You cannot just say, this rock is in thermal equilibrium. Sometimes you will hear that. What does that mean is it's in equilibrium with the environment. We just don't say it, okay? So make sure you know it's comparing 2 objects. So technically, you cannot say, I'm in thermal equilibrium. Or if you say that, we would assume you mean with the environment. And finally, is how do we measure it? Slash heat flow. We know the answer is a thermometer. So what is a thermometer? Let's define it once and for all as well. I'll draw a big picture. Let's say it has a column of mercury inside, or any liquid, like this. Right, so first of all, the layer has to be very thin, so it can conduct easily. And then what you need, so that's what you need, criteria number 1. And criteria number 2, you need a fluid that expands easily. So when you touch on something, the volume, so the volume would, so when it's contact, through conduction, then the volume of the fluid will increase. And then using the second law, right, because of second law, the heat will go from high temperature to low temperature, or the Zeroth Law. And then you use the Zeroth Law to say that, okay, once this happens, you're confident that the T of the thermometer is the same as the T of the system, right? So combining second and Zeroth Law, you can measure, right? You can quantify when something means it's the same. Measure temperature. Okay, so this is the end of our chapter over here. Like, yeah. So one word of motivation is now next thing we want to find out. This begs basically the next question that leads into the next chapter is how much volume would increase when we heat it up, okay? When we apply heat, when we change the temperature like that, right? So this, because things will expand, and fluids and anything will expand when you heat things up. So when you, so the question is, how much? Can we calculate this? And you can. That's the topic of next lecture. Okay. All right. Thank you very much. I just finished on time, so I should finish a little earlier. Still apologize for that. I'll work towards it. Hopefully, this is an enjoyable lecture. Now, I will stay on to record a few extra comments about admin stuff. So if you are not in a rush, you just want to listen to me talk about a few things, I will write down the agenda here so you can decide if you want to list there or not. And if you want to, that's great. If not, it'll be available on Yuja. Okay. So you're welcome, guys, and I'll continue. Yeah. So for those who have to leave, yeah, see you next time. Let's see how much I can do. Let me talk about world's longest straw first. Let me call this an extra example to the fluids chapter. And my question is very simple. I want to ask, what's the world's longest straw you can create? Right, so if this seems interesting, stay for a few more minutes, or you can watch the recording. All right, so what do I mean, right? So I can, if I have a, let's say I have a can of Coke over here, and I am standing on a balcony somewhere, and I'm being extremely lazy. So I decide to make a straw to drink from this Coke because, you know, who wants to walk downstairs when you can consume calories while sitting down? You want to do that, and you wonder, well, what's the longest straw I can make? Well, first of all, you have to understand how straw works. It's not that difficult. How straw works is, well, if you have water, right, you put a straw over here, and what you do is, at this point, you create a low pressure by sucking on it. How do you create a low pressure? By sucking on it. What happens is, so this is your mouth, this is your body, this is your lungs, this is your diaphragm. Sorry, this guy's not having a very good posture. Right. Slightly better. So you have your lungs, you have your diaphragm. Your diaphragm goes down. What happens is the volume increases. When the volume increases, the pressure decreases. Why is that? This is actually, go and explain this later. When volume, I mean, it's obvious. It's intuitive, I should say. All right. So you create a low pressure, good. And then what is the pressure over here? The pressure here is atmospheric pressure, right? Why is it? Because if you zoom in, this point is atmospheric pressure. So if you increase the lung lung volume, you will create a pressure lower than atmospheric pressure. And remember, if you have something lower, you will have, things will go from high pressure to low pressure, right? So this object will have a pressure gradient, and then you will create a force due to that pressure gradient, right? From the pressure gradient, from delta P, sorry. Why is these 2 points the same pressure? We learned, well, equal level is equal pressure. Right? These are at the same level. Anything at the same level has the same pressure. You learned that, right? So as long as you create a lower pressure, then you can suck it up. Now, another thing is you learned is the straw being slanted has nothing to do with how high it can go. It is the perpendicular height that matters. So immediately we can simplify the problem into not worrying about how lengthy it is, but just worry about how tall, what's the maximum height it is. Turns out the answer, so let me give the answer right away, is 10.3 meters. It is impossible, as I'll show in the next few minutes, impossible to go higher, construct a straw that works higher than 10.3 meters. okay? And you realize slanting it or directly, it's nothing to do. It's the same theory. So we're going to analyze the vertical one. All right, so how do I analyze this? So you draw a free body diagram, believe it or not. What is the object of interest? What are you interested in? I'm interested in how far the fluid can go, right? So when you suck on it, so this part is your mouth, right? This is the point. I'm not going to draw the part that it's connecting into your mouth. Just want to worry about the vertical part because, you know, once it goes up, when it go horizontal or go downward, it will continue to flow. You just need to get it up to that level first, right? And then this is the rest of the water, right? Like this. All right. Let's draw. What is I interested in? I'm interested in is the water. Okay. So we need to draw a free body diagram on the water. Draw the center of mass. Right? Everything starts from center of mass. Contact force. What's in contact? Well, this is in contact with the fluid here, which is given by this part will push, right? It'll give a force upwards because it's in contact here. So this normal force going upwards is pressure times area, right? Pressure of the bottom. Now here is contact with the air in lungs. Okay, so when you contact with another fluid, air is a fluid, remember, you have another force. Let's call this N bottom, N top. It's the pressure from the top times the area. So the bottom is atmospheric pressure. The top is lower than atmospheric pressure. Let me call it the lung pressure. Right here, let's say this is the pressure you can create from your lungs. Now, what's the minimum pressure you can create? Actually, so there's an easier way. You can use the idea of pressure gradient and not draw two forces. You can just realize, oh, this is high pressure, this is low pressure, so I can just write one force. So this is pressure due to the pressure gradient, right? So that will be automatically this one subtract by this one. Let me draw a longer one for the top one because the pressure is larger on the bottom, right? So you will have a larger normal force from the bottom. Look how subtle this is. Let me take the chance to comment on this. The arrow pointing up is N bottom. The arrow pointing down is N top, not the other way around. It's easy. You might think this is N top, this is N bottom, right? This is on top, the arrow pointing top, this is bottom. No, it's N on fluid from bottom water, bottom contact. This is the normal force on the fluid from the top contact, okay? So it's not intuitive, but once you get used to it, it should be correct every time. All right, so the contact force is air in lungs and the water at the bottom, right? So this gives you a pressure gradient, which creates the contact force and non-contact force. Anything else touching it, the walls of the straw, but that doesn't make it go up or down, right? The walls does not do anything. The non-contact force is the weight, right, of gravity. So you can now add gravity. And if you want this to happen, you need, what do you need? You need the upwards force to be larger or at least equal to the downward force, right? So you can actually say you need that, that's the minimum, right? But let's say larger, okay? So let's first solve equal. Technically I can go with the inequality, but usually people are less comfortable with inequality than equality, so it's easier to solve this way. What's F up? Well, that's the pressure gradient times area. This is mg. M of what? M of the fluid, right? M of the water. What's the area? Area of the cross-sectional area of this. This is the contact part. So the area of the straw, and the pressure is P2 minus P1, where the larger one subtract by the smaller one. And here, the mass of the fluid, this is the standard trick. You can write it as the density of the fluid times the volume of the fluid. And the volume of the fluid is a standard trick. You can write it as area times height. Notice how the height now comes into my equations. And then now the area on both sides cancel. Now this is the high pressure minus the low pressure. What's the lowest your lungs can go? Let's be very ambitious. Let's go all the way to vacuum. So let's actually, I know it's unrealistic, but that's the minimum, right? You can't go less than vacuum. All right, so this side would become just P2 times, or let me say P atmosphere minus P lungs. And that would be just P atmosphere minus 0. The A cancels, so we have rho H. Let me put this around, rho GH. It looks familiar, but it comes from a different context, okay? What are we trying to solve? Remember, what is our aim? Our aim is to find out height max. So let's solve for H, which is 0. I'll just keep that in for here, rho F times G. you'll see that P atmosphere is 101 kPa. I'm not going to write PA, but I need to write K because K is not the base SI unit, but PA is, Pascal is. Minus, what's the minimum of the lungs? It's 0. What's the density of the water? 1,000. What's the gravity? Roughly 10. Look, 1,000 cancels out 1,000. And then now I just have 101 divided by 10. What's 100 divided by 10? It's 10. 101 is a little bit more. There you go. Now, if you change everything back to inequality, right? So technically, this should be 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 this. Now, the H is on the smaller side, right? I'm moving the thing to the other side, so this is smaller. So look at the conclusion. H is smaller than 10.3. 10.3 is the maximum straw can go. All right, so that's the end of it. Thank you for sticking with me. This is very interesting. Once the quarantine is over, if you like, what you can do is go outdoors and try to. So I've seen people able to suck. There are YouTube videos on this. Actually, let me link you a few interesting YouTube videos. People trying to suck liquid higher than 10 meters. It's quite impressive. People can stand up to like 6 meters and still almost get the. Of course, if you can create a vacuum in your lungs, you probably have a bigger trouble than just drinking the water. But yeah, you can see this playing out in real life. All right. Okay, so hope you find this interesting. Oh, sorry, there's a question. 101 divided by 10. Yes, it's 10.1, but remember I used, so G is 9.81. Plug that in the calculator again, and you should get some. Also, atmospheric pressure is 101.3 kPa. Okay, but the 0.3 is not as important. The 9.8 is more important. All right, good question. All right, thank you very much. Okay, see you guys tomorrow. Bye. Okay. You have a test tomorrow coming up at discussion session 12. So I want to give you my final, I don't want to delay this advice anymore. So I want to give you a study advice on how to study for the test. Sorry, this was my scratch work. It's a bit more messy. All right, so I want to talk about how to use the syllabus to study for the tests and the exams. And then I will share with you my steps, what I suggest, what are the actual 6 steps you go through to study. And then I want to also, because this is to address the Piazza question, a lot of people ask about the Archimedes crowns problem. So I want to record a quick description of how to do that. So again, if you just want to listen to the first 2 advice and stay for that, that's good. And you want to leave after that, that's fine. But these are the things I want to address. The crown problem, what is normal force, what is apparent mass, what is apparent weight, and what is weightlessness. And also, I'll discuss another example of world's longest straw. So I anticipate the whole thing would be around, I'll end between 10 a.m. Okay, that's my expectation for another half hour, 25 minutes. Okay, so the syllabus, I want to talk, so if you never do this, so this is how, I want to share with you how I designed the course, how I expect you would, the ideal way to study. So if you follow this way, it's sort of in line with how I expect you're gonna study. So it might be the best way to come out for you. You have the best effect. Now, do you have to follow what I'm going to suggest with the next 6 steps? No, because everyone studies differently. I'm going to show you, if you like my lectures, how I describe things and understand things so far, this might be beneficial to you. So that's all I said. My philosophy is if you can understand the stuff well, I have a certain goal, what I want to test out of you guys, learn how to do the problem solving skills, right? You see 80% of a 5-point scale is dedicated to showing understanding, and only 20% is about plug and chug, right? So that is my goal of what I want you to get out of the course. That's why I'm testing it that way. And now I'll show you how to succeed in that way if you want to. So syllabus is basically serve that purpose, at least the topics over there. So you see, now we have finished part 1 on fluids. So the syllabus will basically give you a list of topics, right? And it tells you the sequence of how I go about, and it gives you the big picture. So this would give you the understanding part of things, okay? Not the practice, so you need to supplement with that. However, there's so many people who, as I mentioned in the beginning of today, there's so many students find physics difficult because they skip the understanding part and jump to the problem solving part. It seems like a shortcut, but there's the saying that, people say the longest way to get from one point to another point is a shortcut. Let that sink in. So believe me, if you put in just a little bit of, if you just change your mindset to think about, I want to understand things first, then I'll figure out how to solve the problems. Will solving problems be difficult? Yes, it'll still be difficult because it is fundamentally 2 different skills. But will it be less difficult? Yes, I fully believe this. And you're making your life more difficult if you do the shortcut, jump over that step. Or I'm not saying, I'm sure, I've actually seen a lot of great attitudes. You guys were emailing me or actually direct messaging me, or even in Piazza asking great questions. So you're doing great. That is precisely what you want to do. So the second way, not only it's more tougher on you, secondly, you'll find it more boring. You'll find physics a torture. And I don't blame anyone who finds physics torture so far, because that might be how this is something that other professors don't talk about in some force. That's one of the reasons why I want to talk about. So sorry for keeping some of you a few extra minutes, but I think it's something that's not talking about enough and causing a lot of people to cause a lot of stress and pressure. I have to stop using that pun to physics. Yeah, so it's more difficult if you want to do the shortcut. It's less fun, right? It's much less enjoyable, and also you learn much less out of it, right? What do you get out of college after you get your degree? The ability to plug and chug. I can write a program in 10 minutes that do a better job than what humans can do, right? So if you want to be able to not be able to replace by machines, and you actually want to get something good out of college, this is, I think, the ultimate goal. And it's not saying physics is, the holy grail of learning, right? If you take a literature course in one of your electives or optional courses, you learn the different skills to learn how to analyze human nature in a very poetic way. That's another skill you want to take out of it. It's not about learning all the poems. It's not about reading Great Gatsby. I have flashbacks about that, but so hopefully this is the general philosophy. I'll move on to the next point. Student learning objective is if you scroll down. So the first part of the detailed topics gives you the big picture. So when you are learning things for the first time, you're always in the forest, and you might be blinded by where are we going with this, and it's very difficult to gain understanding without the big picture. So that's that job. Now for exams, you want to scroll down to almost a repeated of the table, but with a little bit more words, as you can see. So you can see here, it says, for example, definition of fluid density and specific gravity. So these are things that if you need sort of a complete list of what are the key new concepts, i.e. definitions, i.e. things that might show up in the short answer part, I'm not trying not to give anything away, but it could be define specific gravity. So 2 points. If you write down the equation, define a variable, or write that in words, the relative ratio of the density of an object with respect to some reference material, often water, done. Right? Yeah. So that's that. So now you have an idea of so this is basically how you want to use this to study. Is a checklist. So you want to study, once you know your topics, right, you have to maybe leave by the end of tonight. You probably will spend the afternoon sort of doing some revisions, doing some studying, right, doing some reading. And by the end of tonight, you might want to go through this checklist and see, can I do this? Basic concepts. So do I feel that this is a little bit more vague? Granted, can I solve problems using this? So that part is to how confident I'm. So this gives you a guideline of what should you expect of yourself. This is what I expect of you, and as a result, you can test yourself. Do I know these things? Do I feel confident with it? Right. Right, so that is that. So these are the key lessons, right? So the definitions, concepts, or problem-solving skills, like that. So I might also make minor adjustments, as I was saying, because as I go, I might shuffle things around. So either what you should do is either directly download this from Canvas every time, you'll get the newest version, or if you download this already, I have the version date over here. So if you have a local copy, just compare and make sure you're using the newest chapter. I might add little notes or stuff like that to here. Personally, I like to download things because my internet's sometimes not very stable, and I hate it when things don't load. But if you just take it from the lecture every time, from the Canvas every time, it'll be always the latest version. All right, so the steps to study is this. I will break it down into 6 steps. So the first step is come to lectures. I know there's some restraints, some people cannot make it, right? Then, the next best thing is watch the recordings. So that gives you the first pass of your knowledge, okay? So so ideally both. I will show you if you come to lecture, use the recording as a review, okay? That's why I was trying to make the timestamps. Okay, never mind. Just so that if you realize after you are in step 3, you study something and you realize, oh, I don't know what that means. I want to hear the explanation one more time. Then it's easy. You just look at that chapter, that subchapter, click on that, and you can just watch the 3 minutes on that part. I hope that's that's useful. In a few weeks, I'll ask you guys some feedback if you find that is something worthwhile to do that I should keep doing for the rest of the course or not. Yeah, ideally both. Use recording for review. And then after the lecture, you should do your self-reading. And this is also very important, okay? So this is what I call the learning phase. And then you do the homework, which is testing your understanding. The practice phase, which should serve the purpose of testing your understanding. Now, this is very important because there's two ways I can do lectures. One way is I will just boringly tell you everything you need to know, all the information step by step. That is basically, if you ever had poor lecture experience, again, I'm sure this doesn't happen in UCI, that is a style of teaching where you just, the lecture is the same as the textbook. So at least I find it boring. That might be me, you might find that fascinating. What I like to think of how I treat lectures, this will give you an insight of this, is I treat lectures as watching a movie. Granted, maybe a less enjoyable movie. Hope I'm not making this as fun as possible. Or a documentary. Let's say you're doing history and you take a course, you want to do it, you need to do an exam in history. Isn't it much cooler if you watch a movie first, or the next best thing, watch a documentary? Even how much better is your study? So that's what I want to do, right? Believe me, I was in your shoes, right? I'm a student, I've read textbooks before, and that is the most boring, not the most boring, some textbooks are very well written, but a lot of times the textbooks are not the most exciting things. So what I want to do with the lectures is not give you all the information, because I can either do one or the other. So I'm choosing to do the latter. I'm choosing to present this in a way that it relates to real life, to make this, to tell you why this is interesting. Think of a documentary, that's what they're doing, right? Why a certain thing is interesting, why you should care about it, right? What it is, what does it do, why you should care about it. It's doing that job. But can you watch a documentary and go and immediately write a paper on World War II? Let's say you go and watch Dunkirk, and then if you learn about doomsday and you want to, you need to take an exam on that, that would be a very good thing to do before you go and study and read the textbook, but it's not the ultimate thing. So that's how I want to treat these things. There's a lot of physics documentary, but not, so there's, popular documentaries, and then there is proper hardcore lectures. I want to do something in between, right? It's not as fancy as a popular lecture. I don't have a team of graphic designers, so I wish I can. Someone wants to do that and collaborate, let me know. It's not as fancy as that, but it's not as the other way around. So I want to do something in the middle, so that, by the way, if you see any documentary, that's why I always encourage YouTube videos as well. If someone else have a greater graphic skills and have great explanations, watch those first, and then come back to my lecture. So to go in that level, it's like watching a movie first and then watching a documentary and taking a lecture. It will be much more enjoyable. But the downside is this will rely on you doing a little bit of work. But I don't know how many of you actually follow these two steps so far. If you've done this, I hope you realize that after coming to lectures first, your reading becomes much more enjoyable. Try to read the chapter in advance. Say, determine what is it different after you come to a lecture and then read the material. Okay. Yeah, the downside is you do have to do this, but on the other side, my upside is it actually teaches you to learn, to self-learn. Back to what my philosophy is from the first lecture. Okay. So I think it's all win-win-win. And then you do your homework, which practices your understanding. And then this is the part where you have handed in your homework, right? Now, what do you do with Monday and Tuesday morning, right? So this is what I would suggest you to do, is to review. Spend a little time, to read the chapters that I quoted today as well. But I know everyone's worried about their exam. Here, I'm speaking as if I don't care about exams. I don't care about GPA. I'm being idealistic. All right, now let's be practical, right? So when you review, what I would suggest to do is several things simultaneously. I would suggest you to do extra problems. I would consider homework as a minimum of getting somewhere like a solid B or C. So it depends on how well you understand the homework. If you just do it and you don't understand it, of course, that's not helping. If you do it and you actually understand it, I can guarantee you get a solid B. If you want to push it to an A, this is what you need to do if you're aiming for A. Sad news, unfortunately, believe it or not, you would have to put in extra work to get A. That's what it stands for, A for extra. So when you do extra problems, you will realize, actually, even when you do homework and you will realize, you will find out what you don't know, what you don't understand. Because when you watch a lecture, you watch a documentary or a movie, everything is so logical. You hear me do an example in class, everything is super logical. All right. But when you do it yourself, you realize suddenly you have 24 questions, right? So that's where you need to review. How do you review? Review your notes, and then the lecture recording. This is where I was for those who can tune into the lecture, this is where I encourage you to use lecture recordings, right? You don't know, you take lecture recordings and other resources, and then the book, and then other, right? Other means websites. In the 21st, we're in the 21st century, in 2020, for God's sakes, there's so much knowledge in the websites, YouTube, other resources. Use them. It's about self-learning. That's what I want to promote. All right, and my job is to help you through the process. And then do this first. I encourage you to do this, although you can jump to the next step, which is ask, which I've created platforms for you to be able to do that. Piazza should be your first goal. The second goal is as TA, and the last should be me. Yeah, so ask, and then, but hopefully you do your own job first. Don't just spam this. Although you can, there's no police trying to watch you for that. But for your own sake, you want to be able to be self-dependent. So see if you can do that yourself, and then ask. That'll be even better. You'll get a better understanding. It's not really just for for aesthetic or whatever. It's for you. And finally, extra problems. And now, so this part is where you fine-tune your understanding. So the fine-tune understanding or solidify. This is solidify your understanding phase. Okay. And once you're all comfortable with this, then you're ready for the exam. Okay. So how much should you do? I have no answer for that. Depends on person. I would say as long as you do it until you're comfortable, and then that's the best way.